Hello everyone. So in previous lecture we explored proportional logic, that is how we can represent the facts using simple true or false statements. But proportional logic has limitations. It doesn't allow us to express more complex relationships or refer to specific objects or individuals. So this is where the predicate logic, is also called as first order logic, comes into play. So this predicate logic extends proportional logic by allowing us to represent not just isolated facts but also objects, their properties and relationships among them. It brings structure to our knowledge representation and gives us the tools to represent complex environments logically. So for example, we may want to say all kids are naughty. In predicate logic, we can say if Ali is a kid, then Ali is naughty. So we can represent both the class. Kids, the individual, that is Ali, and their relationship, so being naughty. So now see the syntax, how we build the expressions in predicate logic. So in first order logic, the basic elements are constants, so which refer to specific objects like Ravi or Paris, variables which represent any object like x or y, predicates which represent properties or relationships like is tall or brother, and functions which return objects from other objects like father of, and connectives such as and, or, implies, and negation, not. Finally quantifiers, so which we will see in coming slide shortly. Okay, so all these elements combine to form atomic and complex sentences. So atomic sentences are the most basic expressions in first order logic. So these are formed by applying predicates to a set of terms. So for example, Ravi and Ajay are brothers. It becomes brother of Ravi, Ajay. Okay. Then another example is Chinky is a cat. So it becomes cat of Chinky. So now if you want to make more expressive statements, we create complex sentences. So these are built by combining atomic sentences using logical connectives. Okay, take this as an example. Saranan takes AI if and only if he doesn't take CN. Okay. So this becomes it takes of embraces Saranan comma AI. Okay, it implies or biconditional negation takes Saranan comma CN. Okay. This is that example. Okay, so we'll see here the first order logic gives us the power to represent such conditions with precision. So each first order logic sentence has a subject and a predicate, just like in natural language. So if I say, you can see here, Reshika is a good girl, then Reshika is the subject, is a good girl is the predicate. So in logic, this would be expressed using a predicate function like good girl of Reshika. Okay. So here we will be seeing the breaking down the natural language into components which can be interpreted logically. Okay. And then we have certain other examples. If I say Rekha and Reshika are sisters, we express that as sister of Rekha, Reshika. So, and then we have if puppy is a cat, it becomes cat of puppy. So now consider the complex sentence with connectives. So if we say if it rains, then the street will be wet. So we express that with implication. Rains of X implies wet of X. Okay, this first order logic allows us to express these kinds of relationships across many domains. Okay. Next, other critical advancement of first order logic over proportional logic is the introduction of the quantifiers. So we have seen this, but we'll see in detail now. We have two main types here, that is universal quantifier and existential quantifier. So universal quantifier is represented as for all, this symbol. Existential quantifier means there exist. Okay. So if I say all humans are mortal, we write it as for all x, man, human of x implies mortal of x. Okay. And if I say some students are intelligent, we write there exists x, student of x, cap, disjunction, intelligent of x. So quantifiers which allows us to generalize and specify facts about the group of individuals rather than each one explicitly. So here are some of the examples of the by using the quantifiers. So this sentence is all birds fly, and how we represent that in the first order logic is for all x, birds of x implies fly of x. And similarly other examples. Here not all students like both mathematics and science. So not all represents will be represented by negation. Negation for all x, student of x implies like of x comma mathematics, cap like of x comma science. So these are the some of the examples. And then we have we'll take other examples for representing there exists. Okay, so everyone who studies hard will pass. Suppose this is an example, and also you consider there is a cat on the roof. So how will you represent? By using the quantifiers, both there exist and for all quantifier. Okay. So some more examples you can work out in this to understand better. Then inference in first order logic works similarly to the propositional logic. So but with added richness due to the variables and quantifiers. So just like before, inference helps us to derive new truths from the known ones. So here we have some inferences rules which include universal generalization, universal instantiation, existential instantiation, and existential introduction. So here first universal generalization. If something is true for a specific individual, we can generalize it under certain conditions. Okay. And then universal instantiation. So if something is true for all, it must be true for anyone. And next existential, we have examples for that, how this will be sorted out. Existential instantiation, if something exists, we can treat it as a specific constant temporarily. And existential introduction, if something is true of an individual, we can assert that something has that property. Okay. So we have some examples of the inference. So if I know for all x cat of x implies animal of x and cat of whiskers, then I can infer that animal of whiskers using universal instantiation. Similarly, we can denote that by using the existential instantiation. We replace an existentially quantified variable, that is there exists, with a new constant. Okay. Similarly it goes on. Next we'll see for the generalized modus ponens. So this is an extension of the modus ponens that we have seen in propositional logic, but now applied in the context of the quantified variables. So if we know, for example, for all x student of x cap kind of x implies intelligent of x. So for the first example, and also no student of Lata and kind of Lata. Okay. Second example. So we from this we say that intelligent of Lata. That is Lata is intelligent. We can infer that. So this generalization allows AI systems to apply learned rules to new individuals dynamically. Okay. Next, another concept is in first order logic is the unification. So unification is the process of making two logical expressions identical by finding a suitable substitution for their variables. For example, if you try to unify king of x and king of John, okay, so we find the substitution as x equal to John, that makes them equal. So this is called the most general unifier, that is MGU. Unification is used extensively in automated reasoning and pattern matching. Okay. It's an example of resolution in first order logic. So how this resolution works? So you know that resolution is a powerful inference technique used to prove the satisfiability of logical statements. So here the steps will include, so first conversion of facts into first order logic. So that is first step, convert all first order logic statements into conjunctive normal form, negate the statement we want to prove, use resolution rules and unification to derive a contradiction. Yes, so these are the steps for resolution. And for instance, if we want to prove you will enjoy, and we know certain facts about the weather, we can now again we have to convert these facts into first order logic, transform them into conjunctive normal form, and then negate the joy is the third step. Then derive the contradiction, thereby confirming that the original statement. So this is how theorem proving works in AI. So here a real world example proving John likes peanuts. That is the goal. So we were told that John likes all kinds of food. Peanuts are food. Anil eats peanuts and is still alive. Anything you eat and don't die from his food. So Harry eats everything, Anil eats. So these are the some of the known truths which has been provided to, that is to prove the goal statement. So from this we are expected to prove that John likes peanuts. So how will you do this? We do this by representing each statement in the first order logic and then converting them into uh, conjunctive normal form, applying the resolution systematically. Okay, and then finally eventually we will derive the conclusion that John doesn't indeed like peanuts. So this shows how logic can help machines simulate the human detection. Okay. So you can try this, try converting the real world knowledge into first order logic yourself. So start simple statements about the family, food or habits, and then try inference on them. Okay. So predicate logic is a foundation of many AI applications, from knowledge-based systems to natural language processing. It allows machines to understand, reason, and draw conclusions about the world with structure and accuracy. Okay. Thank you.